When we talk about ideal gases, we're making a couple of assumptions that are not necessarily really true. We're going to assume that an ideal gas has no volume. Not that it's in no volume, but the particles of the gas molecules themselves. Okay? So the molecules occupy no space. All right? So they're bumping around in a very big container compared to their size. So our container is really big compared to these tiny, tiny little dots that are the gas molecules. And the gas molecules, compared to their size, are separated extremely far apart from each other. And so if we would subtract the volume that the actual molecules themselves take up, it would be very, very small compared to the volume of the container. So under ideal normal conditions, that's actually pretty true. The volume is so small of the actual molecules themselves that when we subtract it away from the volume, unless you have a whole lot of sig figs, you really aren't going to notice any change in the volume. So that's okay. That's a good assumption. And then we're also going to assume that an ideal gas has no interactions when they bump into each other. In other words, the two molecules are not going to attract each other, that they're not going to repel each other, that they're just going to be completely indifferent to each other. Okay? So they're going to come in at high speed. This molecule is going to run here, and this one is going to run there, and they're going to bump into each other and completely no effect from the fact that this molecule has electrons bumping into this one and they're going to repel or whatever. These guys are going to just bounce off at some angle and just keep going as if there was nothing happening between them. Well, this is pretty good assumption too for normal conditions, because these gas molecules are moving at very high speeds. When they bang into each other, they don't really have time to stop and notice that, oh my gosh, you're kind of negative, or you're, this end of you is negative, or whatever. They just don't even notice each other. They just bang and bounce and go on with their journey. However, at extreme conditions, these two assumptions break down. So what are the extreme conditions? Extreme conditions. What are they? So if we have very, very low temperatures, okay? Very low temperatures. What will happen? They will move slower, right? If they move slower, and we're talking very low temperatures, getting down close to absolute zero, we're going to move so slowly that they will notice each other, and the interparticle forces will start to actually have an effect. Interparticle forces generally make them attract each other. They will say, oh, hey, hang out here for a second before you rush off, and that's what happens. So they act this kind of effectively will decrease the pressure, because if they kind of pause for a nanosecond or something before rushing off to the next encounter, then there are going to be fewer collisions with the walls. And collisions with the walls of our container is how we measure pressure. That's what pressure is the collisions of the gas molecules with the walls. And if they're busy interacting with each other, when they do that and they slow down at that spot, they're going to be a little slow in getting to the container wall, and we're going to have fewer collisions. Another extreme that we can have is very high pressures. Okay, what does this mean? What does this do? If we have very high pressures, we are squeezing them together. So we're squeezing them all together really close to each other. So instead of being a container with dot, 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 okay, I hope you can see these dots in the replay of this, we're going to be more like this, where we have dot, 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 dot. And you see that the volume now that these molecules are taking up is pretty high. I mean, it's significant with respect to how big the container is. If we squeeze them together so tightly that the volumes of the molecules actually come into play, then what that does is it decreases the empty space that's around them, right? Okay, we cannot say anymore that the volume of the space around these dots is going to be equal to the size of the container. It isn't anymore because the molecules themselves take up a significant amount of space compared to the size of the space we have. So this effectively decreases our volume that we have. So we have something called the deviations from real gas behavior, and I want to give you an equation that takes care of those problems. All right? So van der Waals equation. And van der Waals equation is going to change the ideal gas law, which is P times V equals nRT. And by adjusting for that changing effect on the pressure and changing effect on the volume that we just talked about. So we're going to take that ideal gas law, I'm going to take the P that we started with, and I'm going to add a term to it. N squared A over V. And that's going to be how I'm going to change the P from the ideal gas law. All right? V from the ideal gas law is going to change like this. V minus NB. So both the P and the V are changed, and then the rest of the gas law just stays the same. A and B are constants, and they depend on what gas you have. So in other words, each gas will have its own constants. So if it's hydrogen gas, you have one set of A and B. If it's helium gas, you have another, and if it's oxygen gas, you have another. But you can just look those up in a table somewhere and plop them in, and N, of course, is the number of moles. So N, instead of appearing once in the ideal gas law, appears 1, 2, 3 times in the van der Waals equation. And the same with volume down here. That V down there is still the same as the V that we're used to using. So this equation helps to account for the differences based on our assumptions not holding true at extreme pressures. So what do we mean by these extreme pressures? Very, very low temperatures, kind of getting down there near absolute zero. And very, very high pressures, what do I mean by that? I mean 200 times the pressure of the atmosphere under normal conditions, or 400 or 600 times atmospheric pressure. Not anything you and I would appreciate being around, of course, but gases can handle it, and this gas law, this new equation, helps to adjust for that. The main thing I want you to get out of this whole thing is what the extreme conditions are and why the assumptions of the ideal gas law do not anymore hold true under those conditions. I probably won't ask you in this class to manipulate the van der Waals equations. All it is just plugging a bunch of numbers into an equation. That isn't too challenging. But I want you to understand the variations from ideal gas behavior under extreme conditions.